Greetings students, this is 6th online lecture of nuclear physics. In this class, we are going to discuss about nuclear fusion and thermonuclear reactions. After this lecture, you will be able to understand about how nuclear fusion is happening, the difference between fission and fusion, source of stellar energy and thermonuclear reactions. In nuclear fission, we have discussed that a heavy nucleus breaks up into two fragments with an energy release of approximately 200 million electron volt per fission. This power has been harnessed and is now a reality. We have a lot of nuclear fission reactors worldwide. A process just opposite to nuclear fission is the nuclear fusion, in which two lighter nuclei fuse together to form a heavier nucleus. Nuclear fusion is not exactly a new phenomenon. It has been generating the power of the sun and the stars for billions of years. Before the discovery of nuclear fusion, the source of sun and stars were the most intriguing question. As a result, physicists discovered nuclear fusion in laboratory before the discovery of fission. But to be created and control fusion power on Earth is a tedious process while comparing with fission reaction. Producing and controlling nuclear fission reaction is much easier, and that's why fission received much attention than fusion. In this process, two or more light nuclei combine together to form a single heavy nucleus. For example, when four hydrogen nuclei are fused together, a helium nucleus is formed. The mass of the single nucleus formed is always less than the sum of the masses of the individual light nuclei. The difference in mass is converted into energy according to Einstein's mass energy equation, E equal to mc squared. So the fusion process is expected to release a large amount of energy because a part of the mass of the fusing nuclei is converted into energy. The picture shows nuclear fusion reaction between tritium and deuterium. These two fuse together at very high temperature and converted into helium by emitting the excess neutron. During this process, a tremendous amount of energy is released. Let's see the animation in order to understand the fusion of deuterium and tritium. So the reaction shows tritium and deuterium fuse together to form helium-4 along with neutron and a tremendous amount of energy. So now let's see the animation. So here deuterium and tritium fuse together and it forms a helium-5 isotope, radioactive isotope, and its half-life is just 7.6 into 10 power minus 7 femtosecond. It's very short time. So it's immediately emitting the excess neutron to form a helium-4. So helium-4 is formed and a neutron is emitted along with a tremendous amount of energy, that is 17.59 million electron volt. This much amount of energy is released during this fusion reaction. So here deuterium tritium is fused together to form helium-5 isotope, and then this isotope has a very short lifetime and it releases a neutron and helium-4 along with tremendous amount of energy. In another example, deuterium and deuterium fuse together to form a helium-3 nucleus and a neutron released with the release of tremendous amount of energy. A neutron is emitted. So here let us see deuterium and deuterium. These are fused together and to form a helium-3 isotope, and it releases a neutron along with tremendous amount of energy. It is 2.27 million electron volt. The reaction is given below. So in these two processes, the sum of masses of the individual nuclei before reaction is greater than the mass of helium atom. That excess mass is released as energy according to Einstein's mass energy relation. So since colliding nuclei are positively charged and thus have to break through the electrostatic repulsion between them to fuse together, the kinetic energy of the colliding particles must be high enough to overcome this repulsion. So it should overcome the colliding particles. The kinetic energy of the colliding particles must be very high in order to overcome this Coulombic repulsive force. A large kinetic energy means a huge temperature, a very high temperature. So the initial kinetic energy increases rapidly with decreasing atomic number. So the most promising candidates to undergo nuclear fusion are lighter nuclei like hydrogen and helium. So let us now discuss the fusion reaction with an example. So here let us consider a single helium nucleus formed by the fusion of two deuterium nuclei. The given values of mass of deuterium is 2.014 atomic mass unit, and mass of helium is also given. It is 4.0026 atomic mass unit. So with this we have to calculate the energy released during the fusion reaction of deuterium and deuterium. So now let us discuss the problem. So here deuterium, the reaction is deuterium and deuterium are fused together to give a single helium element. So here He4 along with tremendous amount of energy is also released. So the initial mass of two deuterium atoms, let us calculate the sum of the masses of two deuterium atoms. So this is 2 into the mass of deuterium. So that is 4.028 atomic mass unit. Now let us calculate the product mass, that is the mass of helium atom, that is 4.002604 atomic mass unit. It is given already. So now let us calculate the decrease in mass, that is the difference between the reactant mass and the product mass. So this is 0.0256 atomic mass unit. So the energy released, we can calculate 1 atomic mass unit is equal to 931.3 million electron volt. So we can multiply the mass difference into this value in order to get the energy released during this fusion reaction. So that is 23.84 million electron volt. Thus the energy released in this fusion of deuterium is 23.84 million electron volt. So the schematic is also given. Deuterium and deuterium are fused together to give a single helium along with tremendous amount of energy. So this energy is equal to 23.84 million electron volt. So let us now discuss another example. A deuterium reaction that occurs in experimental fusion reactor is H2 within bracket D comma P, H3 followed by H3 within bracket D comma N, He4. So the first sum is A, compute the energy released in each of these, and the second one B, compute the total energy release per gram of the deuteron used in the fusion, and the third one C, compute the percentage of the rest mass of deuteron released as energy, and D, compare uranium-235 fission with deuteron fusion as a source of energy release. Given values are deuteron mass, tritium mass, proton mass, neutron mass, helium and uranium masses are given. So from this we have to compute the energy release and we have to compare the uranium-235 fission with the deuteron fission. So from this problem, out of this problem, we can understand about the amount of energy released in the case of fission reaction and fusion reaction. So we can compare the amount of energy released in fission reaction and fusion reaction, and we can understand which one is producing large amount of energy. So let us now discuss the solution for this problem. So the first one, we have to find out the fusion reaction. Actually the fusion reaction given is deuteron within bracket D comma P and H3. So this is the nuclear reaction. That means the outside of the bracket we have H2. So this is the target, and the projectile within bracket or the projectile, it represents the projectile and eminent particle, and outside of the bracket is the product. So the reactant is H2 and the projectile is also deuteron, that means the colliding particle. So it is between deuteron and deuteron. So we can write the equation like this: deuteron and deuteron. So this is reacting together, that means fusing together. And in order to produce P means proton. So proton, it releases a proton and the product tritium. So deuteron fuse together, and which releases or which produces tritium along with the proton and a tremendous amount of energy. This is the equation given. So now let us calculate the mass difference, that means the mass decrease in the reaction. So delta M is the mass difference, so we can calculate the mass difference. So 2.014 plus 2.014, these two are the masses of deuteron. So two deuterons are involved as a reactants. So here the masses are added, and minus 3.016 minus 1.0078. These are the masses of tritium and proton respectively. So the mass difference is 0.00433 atomic mass unit. So the energy released during this reaction we can calculate by multiplying with 931.3 million electron volts. So that gives 4.032 million electron volt amount of energy is released out of this reaction. So this is the first reaction, and also the second reaction is given followed by this first reaction, that is tritium is again fusing with deuteron, and that gives a helium 4 element along with neutron and a tremendous amount of energy. So let's now calculate the amount of energy released in the second equation followed by the first equation. So the reaction is H3 within bracket D comma N He4. So here D within bracket D represents the colliding particle deuteron, and N represents the eminent particle is neutron. So tritium is fusing with deuteron, and this fusion reaction gives the products helium 4 along with a neutron, and a tremendous amount of energy is released. So we are going to calculate the amount of energy released. So at first let us find out the mass difference between the reactants and the products. So let us add up the tritium mass and the deuteron mass and subtract the helium mass and neutron mass as mentioned in this delta M. So we have got 0.0188842 atomic mass unit. This is the mass difference between the reactants and products. So energy released, we are now ready to calculate the energy released. So energy released is 0.0188842 into 931.3 million electron volt. That gives 17.58 million electron volt. This much amount of energy is released during this fusion reaction. So we have calculated the amount of energy released in the first equation and followed by the second equation. So the first equation is deuteron fusing together and the amount of energy released is 4.032 million electron volt. In the second equation, tritium is fused with deuteron, and in this case the amount of energy released is 17.58 million electron volt. So the total energy release, we have to sum up the energy released in the first equation and energy released in the second equation. So 4.032 plus 17.58. So the total energy released during both of these equations is 21.61 million electron volt. So the first problem is solved. Now let us move on to the second problem. So the second problem is compute the total energy release per gram of the deuteron used in the fusion. So we have to calculate the amount of energy release per gram of the deuteron. So here we know that, let us first see how many deuterons are involved in both of these reactions. So in the first equation, 2 deuterons are involved, and in the second equation it is actually the product of the first equation is reacting with another deuteron. So the first two equations, in the first equation it is 2 deuterons, and in the second equation 1 deuteron is involved. So totally 3 deuterons are involved in these two equations. So here in the second equation, tritium is fused with the deuteron. So this tritium is produced from the first equation. So we have to consider 3 deuterons in order to calculate the total energy release per deuteron. So the deuterons, there are 3 deuterons involved in both of these equations. So the total energy release is from the fusion of 3 deuterons nuclei. So energy release per deuteron is, we have already calculated the total energy. It is 21.61 million electron volt from both of the equations. So 21.61 divided by 3. Then we will get energy release per deuteron. Since 3 deuterons are involved, we are dividing the total energy by 3. So that gives 7.203 million electron volt. And now let us calculate the number of nuclei in 1 gram of deuteron. That is Avogadro's number divided by the mass of deuteron, atomic mass of deuteron. So that gives total release of energy from 1 gram of deuteron. We can calculate this number of nuclei in 1 gram of deuteron into the energy release per deuteron. That means 7.203 million electron volt. So in nutshell, we are getting 2.153 into 10 power 24 million electron volt. Here actually it is 7.203 million electron volt. That we are multiplying with number of nuclei in 1 gram of deuteron. So we are getting 2.153 into 10 power 24 million electron volt. And now let us move on to the third problem. So the third problem is compute the percentage of the rest mass of deuteron released as energy. So we have to calculate the percentage of the rest mass of deuteron released as energy. So we shall calculate energy equivalent of 1 deuteron nucleus. So 1 deuteron nucleus, the rest mass is 2.014 and multiplied by 931.3, we will get the energy released of one deuteron nucleus. So the average release of energy per deuteron nucleus we have already calculated. It is 7.203 million electron volt. So in order to calculate the percentage of rest mass of deuteron released as energy, we have to divide this average release of energy per deuteron nucleus divided by energy equivalent of one deuteron nucleus. That means 7.203 divided by 2.014 into 931.3 into 100. So that we will get the percentage of the rest mass of deuteron released as energy, that is 0.384 percentage. This much amount of energy is released, this much percentage of energy is released for the rest mass of deuteron. So now let us move on to the fourth problem. So the fourth problem is compare uranium-235 fission with deuteron fusion as a source of energy release. So we are going to compare the uranium fission. Per fission how much energy is released, and per fission of deuteron how much energy is released. So we know that in the case of uranium-235 fission, approximately 200 million electron volt is released per uranium nucleus. So the percentage of mass energy release in the case of uranium-235 fission is 200 million electron volt. That is the amount of energy released per uranium-235 fission divided by the atomic mass is 235.0439 atomic mass of uranium-235 into 931.3 into 100. So we are getting 0.09137 percentage. So in the case of uranium-235, the percentage of mass energy release is 0.09137 percentage. This is in the case of fission reaction. So now we are ready to compare the energy release from the deuteron fusion and energy release from uranium fission. So let us calculate the ratio. It is energy release from deuteron fusion divided by energy release from uranium-235 fission. So both the percentages we shall divide in order to calculate the comparison factor. So that is 0.384 divided by 0.09137, that gives 4.202. That means the energy released from deuteron fusion is 4.2 times higher than the energy released from uranium-235 fission. So the amount of energy release in the case of fusion is much larger than the amount of energy released in the case of fission. So now we shall discuss about the source of stellar energy. The oldest known energy sources such as chemical reaction cannot possibly supply this much amount of energy over a long period of time. So in the case of sun and star, it is emitting radiations, heat radiations for a long time, over a long period of time. But the chemical reaction or any other known reactions can't produce this much amount of energy. So another possibility is conversion of gravitational energy into heat. Suppose if we consider. But this also could not give an adequate explanation. Also, it can't provide continuous supply of such a huge energy. So the failure of ordinary energy sources to explain this huge energy released from sun and other stars led to the thinking that the source of energy might be nuclear. The sun is one of the innumerable stars. The sun radiates 3.8 into 10 power 26 joules of energy each second. So this is a tremendous amount of energy release, and no other reactions like a chemical reaction or gravitational energy, these can't explain this much amount of tremendous energy release over a long period of time. So this leads to the conclusion that the energy might be due to the nuclear reactions. The origin of such a tremendous amount of energy is neither chemical nor gravitational, and failure to other sources of energy, the reason for the energy release reaction might be nuclear. The considerations of nuclear reactions act as the sources of stellar energy. Certain conditions must be fulfilled. The reaction must be exoergic, that is, the sum of the masses of the products of the nuclear reaction must be less than the masses of the reacting nuclei. This mass decrement will then yield energy. Reactions involved should be those which could take place at such a high temperatures and density as at the sun and stars. The reacting nuclei should have sufficient abundance at the sun and the stars where the reaction takes place. So the first condition implies that the nuclear reactions of interest are either fusion reactions of light nuclei into a heavier nucleus or nuclear fission or the radioactive decay of heavy nuclei. About 90% of Sun's weight consists of lighter elements like hydrogen and helium in approximately equal proportion. Since the abundance of heavy nuclei on the Sun is very low, the possibility of a fission reaction and radioactive decay is ruled out. Therefore, it's quite inevitable to accept nuclear fusion reactions as a source responsible for huge energy release in the Sun and other stars. The fusion reactions are very much temperature dependent. So, based on the lighter nuclei abundance and their proportionality, it's reasonable to accept the source of energy as nuclear fusion. So now let us discuss about carbon-nitrogen cycle. Since hydrogen is the most abundant element in the universe, the nuclear fusion reactions for this huge energy production must involve hydrogen as reactant. In 1932, a scientist H.A. Bethe suggested two sets of nuclear fusion reactions such as carbon-nitrogen and proton-proton chain reactions as a possible reaction at the Sun and other stars. The carbon-nitrogen cycle is as follows. C612 fusing with a proton, that gives N713 plus gamma radiation. Here N713 isotope formed in the first reaction is a radioactive. It's apt to call it as radio-nitrogen. The N13 radio-nitrogen nucleus subsequently disintegrates as C613 with the emission of a positron and a neutrino by beta plus decay. So in the first reaction, the energy released is 1.95 million electron volt and the half-life of C612 is 10 power 6 years. And in the second reaction, N713, it's a radioactive isotope or otherwise radio-nitrogen. So its half-life is just 9.965 minutes. So it disintegrates into C613 and a positron along with neutrino. And this decay, we know that it's a beta plus decay, emission of positive beta particle. And in this reaction, 1.2 million electron volt amount of energy is released. So here a proton is converted into a neutron by the emission of a positron. That means a positive beta particle along with a neutrino. So this is known as beta plus decay. Here N713. So the nitrogen has 7 protons and its mass number is 13. So this proton number, it emits one positive beta particle to be converted into a neutron. A proton is emitting a positive beta particle in order to convert into a neutron. So in the next case also the mass number is 13. In the case of carbon, the mass number is 13 again. But the proton number is 6. That means one proton is emitting the positive beta particle or otherwise positron, and then it is converted into a neutron. So the mass number is same, but the proton number is changed to 6. And the third equation, C613 plus a proton, and this is fusing together, and that gives nitrogen N714 along with gamma radiation. And in this case the energy released is 7.54 million electron volt. The half-life of C613 is 2 into 10 power 5 years. And in the next equation, N714 fusing with one more proton, and that gives O815 along with gamma radiation. So here the N714, it is fusing with a proton, and that gives a radioactive isotope of oxygen along with a gamma radiation, and the energy released is 7.35 million electron volt. Half-life of the nitrogen N714 is 2 into 10 power 7 years. So here again we have got another radioactive isotope. It is oxygen isotope. So this is O815 and its half-life is 2.034 minutes. So it's with a rich proton number. So it emits it emits a positron in order to be converted into a neutron. A proton is emitting a positron in order to be converted into a neutron. So the mass number of the product N715 is not changing. That means mass number is same, but the proton number is decreased because proton is converted into a neutron. So O815 in this case, the one proton is emitting a positron and then it is converted into a neutron, so it becomes N715. So proton number is decreased by 1, but the mass number is same. So this is undergoing the beta plus decay by the emission of 1.73 million electron volt in this case. And again the N715, it is fusing with one more proton, and that gives C612 along with He4, helium-4. And during this reaction 4.96 million electron volt is released, and the half-life of this N715 is 10 power 4 years. So at the end again we end up with C612. We start the reaction with C612 and we end up with C612. So this reaction is going on in a chain reaction. This is a chain reaction, and in this case 4 protons are involved, and carbon C12 is fusing with protons in order to produce this reaction. So this is a chain reaction. Now the same chain reaction, we shall have a scheme in order to understand the same chain reaction. So here C612 is fused with a proton and it is producing a N713, and here it emits a positron. N713 is a radioactive isotope, so it emits a positron along with a neutrino in order to be converted into a neutron. So one proton is converted into a neutron, and then it gives C613. And C613, again it is fusing with another proton in order to give N714, and now N714 fusing with another proton, that gives O815. Again here O815 is a radioactive isotope, so it emits a positron along with neutrino. And this O815, its half-life is 2.034 minutes. And then it is converted into N715. Again N715 is fusing with another proton in order to give He24 and C612. So again we end up with C612, and this C612 again fusing with another proton, and this reaction continues as a chain. So this is happening in the case of Sun, and it is proposed by the scientist Hans Albrecht Bethe. And this carbon nitrogen fusion reaction takes place as a chain reaction in which 4 protons are involved. In each of these carbon nitrogen chain reactions, 4 protons are converted into a helium nucleus. So here carbon and nitrogen nuclei simply acts as catalysis in the nuclear fusion reactions. Out of this fusion chain, helium is formed and huge energy is released. The nitrogen formed in intermediate steps, but again converted into carbon nucleus. So it should be noted that Professor Hans Albrecht Bethe was awarded Nobel Prize in Physics during 1967 for his work on theory of stellar nucleosynthesis. He was a professor at Cornell University, New York. So in this cycle, carbon-12 acts like a catalyst, as we already discussed. The reaction cycle is essentially the reaction 4 protons, that means 4H1. This is fusing together with the presence of catalyst C612 in order to produce helium 4 along with 2 positron, 2 neutrinos, and then tremendous amount of energy. So let us calculate the amount of energy released in this reaction. So the loss in mass is calculated as follows. 4 proton mass is 4.03 and helium mass is 4.02603 atomic mass unit, and 2 positron, it is 0.001098 atomic mass unit. And from this information, the loss in mass is 0.02756 atomic mass unit. And when we calculate the energy released during this reaction, so the mass difference into 931.3 million electron volt, that gives 27.5 million electron volt. This much amount of energy is released during fusing 4 protons. And it is found that in 1 million years, the Sun loses about 10 power minus 7 of its mass by the above process. Taking mass of the Sun as 2 into 10 power 30 kilogram and its present age as 10 power 10 years, it is estimated that the carbon-nitrogen cycle may keep going for another 30 billion years. So the total energy released in the process is 27.5 million electron volt, and the age of Sun may be, if we take it is 10 power 10 years, it may prolong for another 30 billion years. So this is about the carbon-nitrogen cycle proposed by the scientist Hans Bethe. So Hans Bethe also suggested the proton-proton chain, proton-proton cycle. For quite some time, it was thought that carbon-nitrogen cycle was the main energy source in the Sun. But now, through a knowledge of stellar temperature, it is concluded that the proton-proton chain contributes about 90% of the nuclear energy. Recent modifications of the estimates of the central temperature of the Sun now favor the proton-proton chain. And the thermonuclear fusion of protons is supposed to release the energy in the Sun and in other stars. In the proton-proton chain, two protons first fuse to produce a deuterium nucleus, which combines with another proton to yield helium-3. Two helium-3 nuclei interact and form helium-4 and two protons. These reactions can be represented by the equations. Two protons, H1 plus H1, two protons fuse together, and that gives He22, and that emits a deuteron along with positron and a neutrino. So this is a beta plus decay. The proton is converted into a neutron by emitting a positron and a neutrino. Along with tremendous amount of energy, it is 0.42 million electron volt. And again, this deuteron fusing with another proton, that gives He3 2, and in this case it emits a He23 along with the gamma radiation, and 5.5 million electron volt is released. And again, in this way, many helium-3 isotopes are produced, and helium-3 isotopes, two helium-3 isotopes are fusing together in order to produce beryllium-4 and that is emitting, that's a radioactive isotope that emits helium-4 along with two protons and 12.8 million electron volt. And this proton-proton reaction, fusion reaction, is dominant at temperatures of 10 to 14 million Kelvin. 10 to 14 into 10 power 6 Kelvin. So overall, 4 protons are converted into a helium nucleus. So the overall reaction of this proton-proton reaction, chain reaction, is 4 protons. So in these reactions, 4 protons are involved. So 4 protons are fused together. That gives a helium, He4, along with 2 positrons, 2 neutrino and 2 gamma rays, plus 26.7 million electron volt. So overall, in this proton-proton chain, 26.7 million electron volts of energy is released during this fusion reaction. So these set of reactions represent one possible route through which 4 protons are synthesized into a helium nucleus. Holmgren and Johnson in 1958, they suggested another possible way in which proton-proton chain takes place. There are 3 possible ways suggested overall by Bethe and other scientists. Those are proton-proton branch 1, proton-proton branch 2, proton-proton branch 3. So now let us discuss. We have already discussed proton-proton branch 1 suggested by Hans Bethe, the scientist, and now we shall discuss about branch 2 and branch 3 reactions proposed by Holmgren and Johnson, the scientists. So in this case, in proton-proton branch 2, in this chain, 2 protons are fused together in order to produce a deuteron along with a positron and a neutrino. So it undergoes a beta decay. It produces helium-2 and this is undergoing a beta plus decay. So it emits a positron and a neutrino, and then it gives a deuteron along with 0.42 million electron volt. And this deuteron is again fusing with another proton, that gives He23, and then this He23 along with the gamma and 5.5 million electron volt amount of energy is released. So these 2 reactions, as mentioned in the proton-proton branch 1, the first two equations, and then from which He3 is produced, and it is fusing with He4. He3 is fusing with He4, and this is giving beryllium 47 along with gamma radiation and a release of 1.59 million electron volt. And now this beryllium 47, it is reacting with an electron, it is capturing an electron, and then it is converted into Li37 and release of gamma radiation and a neutrino. This is also called as electron capture or inverse beta decay. So in this case 0.861 million electron volt is emitted. So the electron capture is one proton is capturing an electron, and then it is converted into a neutron and a neutrino is emitted. So that's the reaction we have discussed, Be47. So in this case, one proton in Be4, the beryllium has 4 protons. So one proton is capturing the electron, and then it is converted into a neutron. So now it becomes Li37. So this is inverse beta decay. It's called as inverse beta decay. So in beta decay, we know that it's a negative beta decay and positive beta decay, beta minus and beta plus decay, and this is inverse beta decay. And this Li37 is fusing with a proton, and it is producing He4, 2 He4 elements with the release of 17.35 million electron volt. So this is proton-proton branch 2 proposed by Holmgren and Johnson. And the next reaction is proton-proton branch 3. In this case, suppose now let us take this equation, beryllium 47, and this beryllium 47 produced from the third equation, it is fusing with a proton, and it is producing beryllium 58 along with gamma radiation. And this beryllium 58 is a radioactive isotope, and it emits a positron and a neutrino and converted into Be48. And then Be48, it emits 2 helium particles. So He4, 2 He4 are emitted from beryllium 48. This is the third branch proposed by Holmgren and Johnson. In the case of the last reaction, the total energy released is 18.209 million electron volt. So this is the total energy released through by considering all the reactions of branch 3. So that is 18.209 million electron volt. So in the case of proton-proton branch 2, it is dominant at temperatures 14 to 23 million Kelvin. And in the case of proton-proton branch 3, it is dominant at temperatures above 23 million Kelvin. So total luminosity, it is defined as proton-proton 1 branch that is producing 83.585%. Proton-proton 2 branches, it is this reactions producing 16.4%. Proton-proton third branch, it is producing 0.015% in the sun's luminosity, sun and other stars luminosity. So it is believed that the proton-proton 1 branch 1 chain reaction is predominant at relatively lower temperatures, and chain reactions proton-proton 2 and 3, branch 2 and 3 are at higher temperatures. So lower temperature means it is relatively lower temperature. So that's 10 to 14 million Kelvin. In the case of proton-proton branch 1 reactions, it is dominant at 10 to 14 million Kelvin, but relatively it is lower temperature while compared with proton-proton branch 2 and branch 3. So in the case of branch 2, it is happening at 14 to 23 million Kelvin. Branch 3 is happening above 23 million Kelvin. So this is proton-proton chain 2, branch 2 and branch 3 are happening at very high temperatures. Now let us discuss about thermonuclear reactions. The source of stellar energy is by nuclear fusion reaction, as we already discussed, and two chain reactions were suggested, and those are carbon nitrogen and proton proton. But it was considered based on the evidences, experimental evidences. It's considered that proton proton chain may be the possible reactions happening at sun and other stars. And the temperatures also we have discussed, and the luminosity percentage from the branch of proton-proton reactions are also we have discussed. So the source of stellar energy is by nuclear fusion reaction. This suggests that a large amount of energy can be obtained by nuclear fusion reaction. But it is not easy to fuse the light nuclei into a single nucleus. The main difficulty in the fusion of nuclei is the electric force of repulsion between the positively charged nuclei. This is the main difficulty, so we have to fuse against the Coulombic repulsive force. The equation of stellar structure set up by A.S. Eddington to the sun and other stars, that we will discuss later on. And fusion is possible when the kinetic energy of each of the nuclei is large enough to overcome the repulsion. Fusion reactions can take place only at very high temperatures of the order of 10 power 7 to 10 power 9 Kelvin. Only at these very high temperatures, the nuclei are able to overcome their mutual Coulomb repulsion and enter the zone of nuclear attractive forces. Hence, the fusion reactions are also called as thermonuclear reactions. So, a star is able to control thermonuclear fusion in its core because of its strong self-gravity. Fusion reactions in the core of the sun cause high temperatures which generate strong outward pressures. These act against the sun's own gravity, preventing it from contracting and holding it in equilibrium position. So the equation of stellar structure set up by A.S. Eddington relates the various parameters related to the sun and the stars. The relation explains about the balance of thermonuclear reactions based on the relevant parameters. Based on these equations, stable models of stars emerged with central temperatures high enough to start and sustain thermonuclear fusion. The key role, of course, is played by the controlling force of gravity. The large mass of an astronomical system makes gravity the most important factor in determining its behavior. The thermonuclear reactions at the core of the sun produces high temperatures which generate very strong outward pressure. This outward pressure acts against the sun's own gravity and preventing the sun from contracting and holding the mass in equilibrium. With this high pressure, the sun's mass would have exploded, but it's not. Since temperature and outward pressure created by fusion reaction is very well balanced by sun's gravitational force, large mass and density. So the strong outward pressure is acting against the sun's gravity. Key factor is that the sun's ability to control thermonuclear fusion by its force of gravity. As we have already discussed, the equation of stellar structure relates the gravitational force in the star to the progressive changes of pressure from its center to outwards. So the gravitational force and changes of outward pressure. this equation of stellar structure proposed by A.S. Eddington. So this is relating the gravitational force and changes of outward pressure. And then the key factor is the sun's ability to control thermonuclear fusion by its force of gravity. And as we have already discussed, the equation of stellar structure relates the gravitational force in the star to the progressive changes of pressure from its center to outwards. The magnitude of pressure to density and temperature. It also relates the magnitude of pressure to the density and temperature. And then the fall of temperature towards the flow of energy from the interior to the surface. So the equation of stellar structure relates gravitational force to changes of outward pressure, magnitude of pressure to density and temperature, fall of temperature outwards to the flow of energy from the interior to the surface. So this relation is very important in order to understand the sun's energy and why it is holding with this, how it is possible to hold the massive mass against this fusion reaction. So at the sun and the stars, there are favorable conditions to hold the thermonuclear reactions. What are the conditions? They are central high temperatures, high enough to initiate and sustain fusion reactions. So the first one is central high temperatures. And the next one, controlling force of gravity, the ability of the star to control force of gravity. And large mass. So large mass of the sun and the stars determines its gravitational field strength. So that's all about the thermonuclear reactions. So thermonuclear reaction means actually the fusion reactions. In order to carry out the fusion reaction, we need very high temperature. So this fusion reaction is happening at very high temperature, and that's why this fusion reaction can also be called as thermonuclear reactions. So now let us discuss about hydrogen bomb. So hydrogen bomb is a device which makes use of the principle of nuclear fusion. The very high temperature required for an uncontrolled thermonuclear reaction is obtained by the detonation of an atom bomb. So we need a very high temperature in order to initiate the fusion reaction, initiate the thermonuclear reaction. So that very high temperature can be obtained by the detonation of an atom bomb. So in this weapon, hydrogen is the core. The fission bomb produces a very high temperature at which thermonuclear reactions start, resulting in the fusion of hydrogen nuclei to form helium. Greater energy per unit mass is obtained from a hydrogen bomb than from a nuclear fission bomb. This we have already discussed in the second example, from which we understood that the energy released by comparing the mass of hydrogen, and that means mass of deuteron and uranium-235 fission. Deuteron fusion and uranium-235 fission we have compared in the earlier slides, and in which we understood that in the case of fusion, deuteron fusion, it is 4.2 times higher energy than the uranium-235 fission. So greater energy per unit mass is obtained from a hydrogen bomb than from a nuclear fission bomb. So the energy is much higher. So energy in the order of megatons of TNT could be released from a hydrogen bomb. A hydrogen bomb or thermonuclear weapon uses the energy from a primary fission bomb to ignite a secondary nuclear fusion reaction. This results a most destructive weapon ever created by man. This illustration shows about hydrogen bomb. A hydrogen bomb is otherwise called as thermonuclear bomb or fission-induced fusion bomb. A hydrogen bomb consists of two important parts which are primary detonator and secondary fusion section as shown in the picture. The primary detonator consists of a chemical explosive, that is trinitrotoluene, it is TNT, simply called as TNT, a small atom bomb to trigger fusion in the secondary section. So this is primary detonator consists of chemical explosive and a small atom bomb to trigger the fusion in secondary section. The secondary section consists of a uranium-238 cylinder with lithium deuteride, a dry powder, simply called as DT. Lithium and deuteride, a dry powder containing lithium 6 isotope and deuterium. So this is containing lithium 6 isotope and deuterium. This acts as a fuel to create fusion reaction. At the core of the uranium cylinder, there is a spark plug made up of plutonium Pu-239, which acts as a spark plug at the core of the cylinder. Instead of lithium deuterium, it's also possible to fill the cylinder with tritium deuterium gas as a hydrogen fusion fuel, with the spark plug remains as it is. The primary atom bomb with TNT chemical explosive is kept inside a heavy metal case as shown in the figure. The primary and secondary setup is surrounded by beryllium neutron reflectors. The outer cylinder case is made up of uranium-238. The whole setup is covered by a metal case. The free space inside the uranium case is filled with polystyrene foam. Now let's discuss the working function of the hydrogen bomb. The primary detonator gets initiated by chemical explosive, that is by TNT activation. The chemical explosive compresses fission fuel so that the subcritical mass connected with the detonator gets inserted with the fissionable subcritical mass of uranium-235. About the atom bomb, we have already discussed in the earlier classes. So once the subcritical mass is inserted into the atomic bomb or into the remaining subcritical masses, then it will create, now the total mass reaches the critical state and hence the fission chain reaction gets started. The fission of atom bomb detonation releases high energy neutrons, X-rays and thermal pressure. The neutrons are reflected from the surrounding beryllium liner. We have a beryllium liner surrounding the whole setup, right? And the X-rays and neutrons cause the polystyrene foam to form a plasma. The plasma, neutrons and X-rays then compress the uranium cylinder, and then fissionable spark plug at the center of the uranium cylinder gets compressed and ignited, causing the lithium deuterium to begin the fusion reaction. The X-rays, neutrons cause the polystyrene foam to form a plasma, and then the plasma, neutrons and X-rays then compress the secondary uranium cylinder in the secondary section. Okay, it compresses the uranium cylinder, and then at the core what we have the fissionable spark plug at the center of the cylinder or core of the cylinder. So this fissionable spark plug is now compressed, and then it gets ignited, causing the lithium deuterium to begin fusion reaction. So the plutonium-239 core ignites the lithium deuterium from the center of the cylinder by a fission reaction. The lithium-6 isotope, it absorbs a neutron and transforms to tritium. Then the tritium and deuterium fuse together at this high temperature and pressure created by the atom bomb. So the reactions are given here. Lithium 6, it absorbs a neutron and then it becomes a helium, He4, and it produces a tritium. And this tritium is reacting with a deuterium because deuterium is already there inside the uranium cylinder, and it produces another He4, helium, along with a neutron and then 17.6 million electron volt. So at the end of fusion reaction, a neutron is emitted and that generates tritium, and the process continues until the fuel is available as a chain reaction. The fusion reaction of tritium and deuterium releases helium. That means it releases helium and then a neutron and a high energy of 17.6 million electron volt per fusion. If we compare the percentage of energy release compared to the element mass, the energy released in hydrogen per fusion is 4.2 times higher than uranium per fission, as we already discussed. Hydrogen bomb energy equivalent to 10 megatons of TNT and even above. It's more than an atom bomb which releases energy in the order of few kilotons of TNT. Bombs dropped at Hiroshima and Nagasaki, it's actually explosive energy equivalent to 15 and 20 kilotons of TNT respectively. In this case, 15 kiloton is equivalent to 84 terajoule, or 84 into 10 power 12 joules of energy in the case of 20 kilotons of TNT. 20 kilotons of TNT is equivalent to 84 terajoules. So the first thermonuclear, that means hydrogen bomb, tested by USA in November 1952. The energy release approximately equal to 10.4 megatons of TNT. That means 42 petajoules, 42 into 10 power 15 joules. In the case of TNT, actually it's 1 gram of TNT explodes 4.8184 kilojoules. Thermonuclear bombs are made small enough, a few feet long, fits in the warheads of intercontinental ballistic missiles. These missiles can travel almost halfway across the globe in approximately 25 minutes and have computerized guiding systems so accurate that accurately it can fix the target, and the defense forces can land accurately within a few hundred yards of a designated target. So now this is about hydrogen bomb. Now let's discuss about the controlled thermonuclear reactions. A large amount of energy is released in a fraction of a second in the case of hydrogen bomb. Whereas similar to nuclear fission reactor, if we control the fusion reaction, the nuclear fusion reaction or thermonuclear reaction, if we control, then it's possible to extract a huge amount of energy, huge amount of useful energy for the human society. Fusion reactor is a device within which the nuclear fusion reactions could take place in a controlled manner. Useful quantities of energy in excess of that required to operate the device could be extracted from it. We have already discussed about the release of large amount of energy radiation from the sun and the stars at a high rate is because of fusion reactions taking place in the stellar objects. But these fusion reactions in Sun and other stars take place in an uncontrolled manner, and as a matter of fact, to impose some external control over these fusion reactions is a hopelessly difficult task. If the thermonuclear reaction could be controlled, the energy released can be used for constructive purposes. We know that very high temperatures are needed to bring about a nuclear fusion process. As discussed earlier, for a fusion reaction to take place, the colliding particles or nuclei should have enough energies to overcome the Coulombian repulsive forces between them. This needs energy of the order of zero point 0.1 million electron volt, which corresponds to a temperature of approximately 10 power 8 Kelvin. This means that for a fusion reaction to take place, temperatures of this order should prevail initially. Before starting the fusion reaction, we need to have this much amount of tremendous heat, tremendous energy, 10 power 8 Kelvin. It should be prevailed initially. At such a high temperatures required for fusion, the atoms are completely stripped of their electrons. That is, the atoms are completely ionized and the free electrons move about rapidly. The mixture of electrons and ionized atoms is still neutral. This completely ionized and electrically neutral state of matter is called as plasma. The matter contained in stars, sun and galaxies is in this plasma state and is held there through gravitational force. But the problems of production and confinement of plasma in laboratory are really formidable ones. The main problem is to produce such a high temperature and to find a container for the gas which can stand this temperature. At this temperature, the gas is highly ionized, which is called as plasma. So one of the severe engineering problems is the design of a container in which a very hot plasma can be contained under high pressure to initiate a fusion reaction. Since almost any container would melt in the presence of a plasma, attempts are being made to contain and control plasmas trapped in a specially shaped magnetic field. By increasing the field and changing the shape of the field, it is hoped that the plasma in this magnetic bottle can be raised to the required temperature and pressure for fusion reactions. The figure shows a plasma containment. Actually, this is a tedious task to hold the plasma away from the walls for long enough for fusion reactions to take place at a temperature of 10 power 8 Kelvin. Since plasma contains matter in highly ionized state, the problem of plasma containment could be solved through the application of magnetic fields, and in fact it's the only way. There is no other go. So the basic principle of confinement of plasma through the application of magnetic field is that moving charged particles are deflected from their straight line paths by magnetic field as shown in the figure. A hot high pressure plasma could under proper conditions generate a magnetic field of its own strong enough to exclude the externally applied field. Inside such a plasma, the particles would move in straight lines except at the boundary. From there they will be deflected back into it by the external magnetic field. So inside such a plasma, the particles would move in straight lines except at the boundary. So from the boundary, there from the boundary, they will be deflected back into it by the external magnetic field. So if the magnetic field is strong enough, it will hold the plasma like a bottle holds the gas. So the arrangement is therefore called magnetic bottle. That's why this arrangement is called as magnetic bottle. A fusion reaction sustained in such a magnetic bottle could never run away. If the plasma pressure exceeds the magnetic field, plasma moves to the chamber walls by rupturing the magnetic walls, which immediately quenches the fusion reaction. In the world, fusion reactions are in just experimental stage only. We are still under construction of fusion reactors. So the possible reactions in fusion reactor. The possible fusion reactions that could take place in plasma are deuteron-deuteron fusing together. It produces tritium and a proton with a tremendous amount of energy. It's 4.03 million electron volt. And again, another possibility is deuteron-deuteron. It produces helium-3, a neutron, and 2.27 million electron volt energy. And another possibility is deuteron with tritium that produces helium-4 along with a neutron and 17.59 million electron volt. And again, deuteron with helium-3 that produces helium-4 plus proton plus 18.3 million electron volt. So these four fusion reactions are possible in hydrogen plasma. The other possible fusion reactions take place in plasma are Li36 fusing with deuteron that produces 2 He4 along with 22.4 million electron volt. And another possibility is Li37 fusing with proton that produces again 2 helium-4 along with 17.3 million electron volt. So these are the other two possibilities. So in this case, actually Li6, as we already discussed in the case of atomic bomb, Li6 absorbs a neutron and that produces helium-4 along with the tritium. So this tritium again reacting with the deuterium that is producing helium-4 and a neutron and 17.6 million electron volt. This could be combined with this fusion reaction. So from the second equation, deuterium and deuterium fuse to release helium-3 and a neutron, and that neutron could be utilized to bombard with Li6 to release helium and generate a tritium as shown in the equation. So again, tritium and deuterium fuse to release helium-4 along with 17.6 or 17.59 million electron volt. So in ITER, the International Thermonuclear Experimental Reactor that conducts nuclear fusion research and engineering under a mega project. But before that, let's discuss the applications, and then let's also discuss about the worldwide research undergoing to build a fusion reactor. So the applications are, in the case of nuclear fusion as an energy source, it will be a boon to humanity because of the following reasons. So hydrogen is available everywhere on this planet in various forms, and it's abundant. So abundant fuel supply, that means by deuterium, it can be readily extracted from seawater, and excess tritium can be made in the fusion reactor itself for lithium, which is also readily available in the Earth's crust. The lightness of the reactant nuclei makes the energy yield per unit mass of the reacting material much greater than that in nuclear fission process. If a fusion reactor does not leave behind, there won't be any wastages, radioactive waste like a fission reactor. As in fission reactor, In the case of fission reactor, the radioactive waste and the disposal of which it's a tremendous problem in the case of fission reactor. But in the case of fusion reactor, there are no leave behind, so no radioactive waste, and it's safe, completely safe. The amounts of fuel used for fusion are small and compared to fission reactors. In the case of fission reactor, the amount of fissile fuels used are very large. It's a huge fuel we have to use. But in the case of fusion reactor, the amounts of fuel used are very less. So now let us discuss few attempts or few experiments, ongoing experiments around the world. One of those are ITER. This is International Thermonuclear Experimental Reactor that conducts nuclear fusion research and engineering under a mega project. ITER will be the world's largest fusion reactor which is under experimental stage. ITER is located in Saint Paul les Durance. It's in South France, and ITR are collaborating with 35 countries to build the world's largest tokamak. Tokamak means a magnetic fusion device that has been designed to harness pollution-free energy of fusion. The ITR project worth is about 22 billion US dollar. Tokamak is an experimental machine designed to harness energy of fusion. The tokamak machine will be powered on by December 2025 to harness energy. The design of tokamak is to produce a tenfold return on energy or 500 megawatt of fusion power from 50 megawatt of input heating power. The deuterium tritium operation is expected to begin during 2035 at ITER. So this is one of the nuclear fusion research center, and this is collaborating with the 35 countries to build a tokamak machine. It's a nuclear fusion device, a magnetic fusion device. And Joint European Torus is an operational magnetically confined plasma physics experiment located at Callum Centre for Fusion Energy in Oxfordshire, UK. And JET started conducting fusion experiments with the tritium. It's a rare radioactive isotope of hydrogen. So it started the fusion experiments since 1997, and JET also had a plan to begin fusing even quantities of tritium and deuterium during this year 2021. The temperatures in JET can reach 100 million degrees. ITER is just a translation of JET with some advanced technology, and in JET the inner wall is made up of beryllium and tungsten. And UK nuclear scientists are designing an ambitious prototype facility that could demonstrate commercial energy production by 2040. Today, many countries take part in fusion research to some extent, led by European Union, the USA, Russia, and Japan, with various fusion technology programs in order to make it useful energy, in order to harness useful energy from the fusion reaction that could really helpful for the human society. With this, we have come to an end of this presentation about nuclear fusion. Students, so far we have discussed about nuclear fusion, few fusion reactions, few problems related to the energy release in fusion, comparison of energy release per fusion and fission per fission, source of stellar energy, carbon, nitrogen and proton-proton fusion chains, thermonuclear reactions, hydrogen bomb, controlled thermonuclear reactions in a fusion reactor, design of magnetic bottle to initiate the fusion reactions, applications, and possible researchers around the world to start fusion reactors. Hope you would have understood the concepts. In the next lecture, we will discuss about the accelerators. Stay tuned to learn the concept of accelerators. These are the reference books used. 2 books, articles, and few web references. The books used are Modern Physics by R. Murugeshan and Kritika Sivaprasad, Elements of Nuclear Physics by M.L. Pandya and R.P.S. Yadav, and also an article, The Production of Artificial Radioactivity by Frank Brescia, Robert Rosenthal, Journal of Chemical Education, published during the year 1934. And also I referred a few web sources. So have a great day. Thank you.